Hello, ladies and gentlemen, and welcome to 14.3, which is entitled Wave Behavior. What we're going to be talking today is about how waves behave when they meet a boundary. Now, they could be meeting a boundary that's more dense. They could be meeting a boundary that's less dense. They could be meeting each other. They could be interfering with each other in a very special way, which we call standing waves. And we can even get standing waves on two-dimensional surfaces. So that's kind of the gist of what we're going to be talking about today. So let's get started. I've got a bunch of terms here that I'm going to end up defining as the video progresses. So let's begin. The first thing I got is this is what happens when a wave goes from a less dense medium into a more dense medium. This first wave that starts it all off, it's this wave that's coming down here right now. We call that the incident wave. It's the wave that starts it. It's the initial wave that before it hits the boundary, that's what it is. Now, that incident wave comes down, hits the boundary, and then turns around and comes back on the opposite side. We call this the reflected wave. Now, the wave that goes through, you'll see the boundary here. We'll call this the boundary. The wave that travels through, we call this the transmitted wave. Now, incident wave, reflected wave, boundary, and transmitted wave. So these are words we use to describe when a wave meets a boundary. Now, something that's very important to when a wave meets a less dense medium, it will always come back on the opposite side. We call this inversion. The reflection will come back on the opposite side. Now, you'll notice too that the reflection is smaller. That's because it gives some of the energy to the transmission. You'll notice that the transmitted wave is smaller. You'll also note that the transmission is on the same side. We call this upright. So there's a bunch of terms right there. Next, we're going to have when a wave meets a less dense boundary. See if you can see the similarities and the differences when I go to this one. When you're going into a more dense, from more dense to less dense, first thing you're going to notice is the reflection is upright. It's on the same side. The reflection comes back on the same side. The other thing is it's smaller also. So in both cases, it comes back smaller, and that makes sense because it's giving some of the energy into the transmission. Watch the transmission. The transmitted wave transmission is larger. This has to do with the mass of the medium. It's easier to move this lighter medium, so it will make a larger wave. It's also faster. And it's on the same side. So similarities to going from a less dense to a more dense. The reflection is smaller, so that's the same with our last case. And the transmission's on the same side. That's the only things that are the same. Other than that, everything's opposite. Let's look at the speed on the other one, see if there's a speed difference. Yeah, you'll notice that the transmission's also slower. Harder to move that material, more inertia. All right. Next, we're going to talk about wave superposition. When two waves meet, we call this wave superposition. Now, two waves can come together to make a larger wave, and we call that constructive interference. That's actually what this is. You've got two waves coming together to make one larger wave as they overlap, constructive interference. You can have waves come together, like if you had an amplitude that was positive, like a wave coming in up, and then you've got a wave coming in down, and these two things come together to meet. When they meet, they're going to cancel each other out a little bit. We call that destructive interference. Destructive interference. Now, these waves algebraically add up. So you've got a wave coming in here, that tall. You've got another wave coming in here, this tall. Let's just pretend that this is maybe 8 units tall, and let's pretend that this is 6 units tall. You add them together, you should get 14. And if you were to actually measure this, where these come together, it should be equal to 14. They add together to make the algebraic sum of one another when you have waves coming together. I got a couple videos to show you. Well, one in particular before we move on to standing waves, just an application of wave superposition in wakeboarding.
There's a good chance if you wakeboard, you tried it. There's an even better chance you've been slammed by it. Double ups. It's one of the toughest moves in wakeboarding to master for both the driver and the rider. Let's hand this off to the masters, Parks and Rusty, as they help you unlock the mystery of double ups.
Hey, what up? I'm Parks Bonifay. This is Rusty Malinowski. We're out here on Rusty's
These two of the
Lake
best
right
wakeboarders that ever
and
been.
We're going to give you a couple tips and pointers for doing some double ups. A double up is actually where a boat goes straight and it actually curves around and goes back into its original rollers. The two rollers converge and actually doubles up. This is where it gets even bigger than the normal roller. You see 1080s, double.
Do you see that? These two waves are coming together, and the wakeboard, it's really hard to do. These two waves come together to make one super wave, and you got to hit that wave at just the right time, and oh my gosh, can you get some air when you're doing that?
Flips, and we're going to do something right now, so check it out. So right now I'm going into my pre-turn for the double up. Pre-turns help your lake out because you're not sending rollers all the way back down the pass. So if you do a pre-turn, your lake will stay calmer longer. So now I'm doing the pre-turn, setting up the original roller. You want to make sure the boat is really straight. Any type of like leaning with the boat can dictate how the roller is going to look for the double up. So now I'm going to swing wide for the double up. Wider the better. You can make sure that the boat can get back on plane. You're not accelerating through the double up. You want a really consistent speed, and you want the boat to be level. It also gives you more time to line up the angle of your double up. If you want to open your double up, you would come out of your turn earlier, like this, but if you wanted to tee it up more, you would lean into it more at the end. Try to keep the boat level.
Watch the two waves
Let
converge.
Rusty bang out
Boom!
the blinds
And you hit
all
it at
day.
just the right time, and it is air time. I'll leave you a link to this. This is a pretty sweet video if you want to watch a little bit more. The next thing I want to talk about is standing waves, and I'm going to hand this off to a friend of mine. Her name is Physics Girl. She's kind of new on the YouTube scene, and she's making some really incredible videos, and so I wanted to go over there to let her explain some standing waves, how they work. I think her graphics are great. She does an excellent job, and then we'll come back here to wrap it up.
Hi there! Did you want to create some cool physics art without having to do any of the design yourself? I thought so. We've got the square plate on the mechanical vibrator, which is plugged into the tone generator. This vibrates the plate at different notes as we change the frequency here. I'll sprinkle a little sand on the plate, and now watch this. Why does this happen? As I tune the plate to vibrate at very specific
I have one of these plates. We can
frequencies
play
or
with it.
notes, the sand moves on the plate into beautiful, though unusual patterns. As I find higher and higher special frequencies, the patterns on the plate get more intricate. How awesome is this?
You'll notice their
But it
sand is
does
going
kinda
one way.
sound like
I
a
think it's
dying
because their
ferret.
table's not level.
Why does it happen? The main concept here is resonant modes. Let's back up a little bit to the physics of waves.
In physics, a wave is a disturbance traveling through a medium or through space.
If I constrain my medium at the other end,
The wave reflects back at me.
see? Now, if I send continuous waves down the slinky, they also reflect back, and what I get is two waves, one moving away from me and one moving at me. But obviously the rope can't be in
Now, you'll notice, too, that these waves are encountering a more dense medium. That's why when they reflect back on the opposite side.
both places at once. So as my incoming wave reflects back, I don't see both waves, I see a combination of the two. The waves add when they're on top of each other
Superposition.
and subtract when they're opposing one another. And something crazy is happening. You've got a wave going this way combined with a wave moving that way, and when they interfere, the result is, as you might expect, a wave that doesn't appear to be moving in any direction. It's standing! This is called a standing wave. And so is this. The places where the wave appears to be not moving at all are called nodes, and the places where they're moving a lot are called antinodes. Now that we've mastered standing waves, let's go back to our square plate. If you look closely, there are places where the plate and the sand are moving a lot, and places here where they're not moving at all. These are nodes, just like the nodes that didn't move on our slinky. Here are the antinodes. And just like we needed specific frequencies to get standing waves on our slinky, the same is true of our plate. These specific frequencies are called resonant modes, and they're caused by waves traveling out from the center, bouncing off the sides, and interfering with each other just right so we get standing patterns. Also, the higher the frequency,
Now, the lowest frequency that will resonate, we call that the fundamental. The next one we'll call the first harmonic, and then the second harmonic, and so on, climbing up the scale. So the lowest frequency that will resonate in a medium, we call that the fundamental.
the closer together the nodes, just like the slinky. But now, what if you did this in 3 dimensions? You could have vibrations coming from the sides, spin from the front and back, and you'd get interference from all of these such that there'd be nodes in mid-air, places where the air is completely unmoving, and you could, hypothetically, place an object there and cause it to levitate. That would be crazy. But it's exactly what researchers from the University of Tokyo and the Nagoya Institute of Technology did.
I've seen this. It's absolutely crazy. They're manipulating the nodes in midair so they can move this stuff around in midair. This is dry ice that's evaporating that you can see. That's actually subliming because it's going from a solid right to a gas. An LED. And they can actually move it left, right, up, down, forward, backwards.
Well, that's all I got. Really, the physics is the cool part. So, stay tuned to see the vibrations on these plates.
And it's neat, like the way that your musical instrument, if you play a stringed instrument, I know a lot of you guys play strings, the shape of the body dictates which frequencies will resonate. So if you're playing a G, certain, like the Stradivarius, you've maybe heard of them, it makes them more potent in resonating certain frequencies. Very cool. So I think she did an incredible job of explaining how standing waves work. 2 waves coming at each other. You get the nodes, which are these spots that don't move. The antinodes, those are the spots that move a whole lot. Right here, this is what we call the fundamental, the lowest frequency that will play. Here's our first harmonic right here, second harmonic, third harmonic, and so on, right on up the scale. And then she even showed you 2-dimensional waves, standing waves on a surface. And this plate's vibrating, so you look for the places that aren't moving, and that's where the sand is going to settle. It's going to settle into the nodes. Well, I think that we went over most of these terms. I didn't specifically go and write them all in, but during the spots, I think I talked about all of them. Thanks for watching.